The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, let's start. So first, let me just remind you what we did at the end of last lecture. So we see that the large N expansion of gauge theory have essentially exactly the same mathematical structure with, say, the mathematics of the n-string scattering. And so here the observables are correlation function of gauge invariant operators. And then this have a large N expansion as follows. And on this side, you have just n-string scattering amplitude. Just imagine you have, just have some kind of scattering of strings with total number of n strings. And this also have expansion in terms of the string coupling, and in this form. So now, if we identify, so we can identify this G string with 1 over n. So if we identify G string with 1 over n, then these two are essentially the same kind of expansion. Okay? And you can identify identify these external strings, string state, within the large N theory, which we call the say global state or single trace operators. Or single trace operators. And in each case is corresponding to some over the topology. It's an expansion in terms of the topology. So here is the topology of the worksheet. Of string, and here is the topology of Feynman diagrams. Here is the topology of the Feynman diagrams. So still at this stage, it's just like a mathematical correspondence. We're looking at two completely different things. Or probably there's no obvious connection between these two objects we are discussing. And we just have a precise mathematical structure. But one can actually argue, that actually they also describe the same physical structure once you realize that when you sum over all possible Feynman diagrams, so once you realize each Feynman diagram say of genus H can be considered as a partition, or in other words, triangulation of a genus H surfaces. 2D surface. Okay. So if we write more explicitly this FH, so if we write explicitly of this FH, then this FH, this FNH, then would correspond to your sum of all Feynman diagrams. Say of genus H. say this is the G. Suppose G is the expression for each Feynman diagram. Say for each diagram. Okay. And then I can just rewrite this in some sense as all possible triangulation of a genus G surface. Say with some amplitude, with some weight G. And all possible and summing over all possible triangulations of a surface is essentially, so this is essentially the same as a sum of all possible surfaces. So this is a discrete version. So some all possible triangulations, say of some genus G surfaces, or triangulations of genus G surfaces, then it can be considered as a discrete version of sum over all possible surfaces. Okay.
So you're saying it's like a sum over like simplices, like a simplex.
Exactly. Yeah, because imagine when you sum over surfaces, say you sum over all possible metric, you can put unlit, etc. And that's the same way as you sum over different discretizations of that surface. Once you have defined the unit for that discretization. So if we can identify, so now recall this FH. So this FH, this FNH is the path integral over all genus H surfaces with some string action, weighted by some string action. Weighted by some string action. So if we can say identify, this G with some string action, so exponential of some string action, then we would have, then one can conclude that Nagian's gauge theory is just a string theory, okay? Okay, the Nagian gauge theory is just a string theory if you can do that. And in particular, the Nagian limit. So Nagian limit here, as we discussed before, can be considered as a classical theory of group balls, or a classical theory of the single trace operators. So this will be matched to the classical string theory. So as we mentioned the last time, so I was mentioning before, this expansion, so just as in the as we discussed, the expansion in G string is the same as expansion in the topology. And the expansion in the topology can also be considered as an expansion of the loops of a string. Because whenever you add a hole to the genus, when you add a genus and you actually add a string hole, you add a string loop diagram. So in this sense, you can interpret all these higher order corrections as the quantum correction to this classical string behavior. Okay. So this is just a tree-level amplitude for string, and this corresponding to the loop. So when you add, whenever you add this thing, you add the loop. Okay, is this clear? And remember what we discussed for the torus. Torus, then corresponding to you have a string split and join together, and this and this split and join process you can also consider, say, as a string loop. A single string going around the loop, and just like in the particle case, okay, in the standard field theory case, and so the Largian limit, which is the leading order term here, would map to a leading order in the string scattering, and the leading order in the string scattering they only consider, say, tree-level string scatterings, and then would be corresponding to a classical string theory. And then also the single trace operator here can be mapped to the string states. Yeah, it can be mapped to the string states. Okay? But this is a very nice picture, but for many years this was just a dream. It's because this guy looks very different from this guy. So this is, yeah, but this is difficult. So this signification is difficult. For the following reasons. So first, so this G just say your Feynman diagrams, amplitude for particular Feynman diagram. So G is typically expressed as product of field theory propagators. So imagine how you evaluate a Feynman diagram. The Feynman diagram is essentially just a product of the propagates, and then you integrate it with their vertices integrated over space-time. Okay. Then just take the Yang-Mills theory, and if you look at the expression for those diagrams, of course, you look nothing. So they look nothing like. Okay. So let me make a few comments about this thing, because if you want to match, say if I give you a Yang-Mills theory, if I give you a QCD, then you can write down then you can go to Largian, you can write down expressions for the Feynman diagrams. But if you say I want to write it as a string theory, then first you have to say what string theory you want to compare with. Okay, so first you have to ask yourself what string action do you want to compare. So the string action. So this string action as we discussed last time, this describes the embedding of the worldsheet into some space-time. Okay, so this is worldsheet. Into a space-time. Space-time. So this is always this is also sometimes called the target space. So this is a space-time this stream moves, and mathematically this is just this is encoded in this mapping x mu sigma tau. Okay, x mu is the coordinate for m, and then the sigma tau is the coordinate you parameterize your worldsheet. So in order to write down a string, in order to write down an action, of course, you have to a choice of space manifold. You have to choose your space-time, and also you have to when you fix the space-time, you have to then have a choice. Then sometimes the way to write down this string such kind of embedding is not unique. The action for such embedding is unique, so so you also need to choose what the action you include. And also often, in addition to this this embedding, you can have sometimes you can have additional internal degrees of freedom. Living on the worldsheet. For example, you can have some fermions. Say if you have a superstring, then you can have some additional fermions living on the worldsheet in addition to this embedding. So in other words, the choice of this guy, in some sense, is infinite. And you, without any clue, so you need some clue to know what to compare the gauge theory to. And otherwise, even if this works, you're searching some needle in the big ocean. In the big ocean. And there's another very important reason why this is difficult. Why this is difficult is that this string theory is formulated in the continuum. It's formulated in the continuum. And these Feynman diagrams even if they correspond to some kind of string theory, they correspond to a discrete version of that. They correspond to a discrete. So at the best, it's a discrete version. So we expect the geometric, such a geometric picture for G, for these Feynman diagrams, to emerge only at strong coupling. Okay? To emerge only at strong coupling for the following reason. So if you look at the Feynman diagram, so the simplest Feynman diagram, say we drew before, say for example just this diagram, okay? And if you draw it on the sphere, it separates the sphere into 3 parts, okay? So discretize the sphere into 3 parts, And essentially, just the sphere just becomes 3 points because each part corresponding to, when you triangulate, then each part you approximate about 1 point. So essentially, you in this diagram, you approximate the whole sphere essentially by 3 points. Okay. And of course, it's hard to see geometric picture from here. And geometric picture you expect to emerge when your Feynman diagram become very complicated. For example, if you have this kind of diagram, because of the 4-point vertex, in principle, you can have all these diagrams. And then this corresponding to discretize, suppose this is on the torus. Let's do it on the torus. Suppose if you have, for example, this could be a Feynman diagram on the torus, okay, for the vacuum energy. And now this is like some kind of proper discretization. And this will go to a continuum limit, say when the number of this box go to infinity. When the number of boxes go to infinity, then you need the number of propagators, and the number of vortices go to infinity. Okay? So in order for continuum a picture to emerge, so you want those complicated diagrams with large number of vertices or large number of propagators to dominate. And for those things to dominate, then you need strong coupling. Because at weak coupling, this is the leading order diagram. And there's no geometry from here. Okay? So in order to have the geometry, you want the diagram very, very complicated so that they really corresponding to a fine triangulation of a surface. A weak coupled diagram with small number of lines will correspond to a too crude, will correspond to a very close triangulation of a surface. So we expect this only appears as strong coupling. Okay?
But the case is like we have to sum over all the Feynman diagrams.
Yeah, sum over the Feynman diagram.
Including those simple ones.
Including those simple ones. So that's why you want to. So if you're in a weak coupling, then the simple ones. So in this diagram, so when you sum all those diagrams, each diagram you can associate with a coupling power. Mm-hmm. So at the weak coupling, then the lowest order term will just dominate. And the lowest order term have very simple diagrams. And then that's corresponding to a very crude triangulation of the surface. But if you have a strong coupling, then in particular, if you have infinite coupling, then diagrams with, say, infinite number of vortices will dominate. And then that's corresponding to a very fine triangulation of the surface. And then that can go to the continuum limit.
But the interaction, coupling constant has been dragged out from. Okay.
No, that's just n dragged out.
Oh, I see.
No, this is what we call this 2 Hooft coupling still remaining.
Okay.
Yeah. By coupling, it's only n.
Coupling is not a coupling. It's like
No, this is a 2 Hooft coupling. Strong coupling, we mean the 2 Hooft coupling. So example we talk about corresponding to this lambda. And let me make more precise. So in the toy example we talked about before, so previously we talked about this example, n divided by lambda trace, say 1/2 partial phi square plus 1/4 phi to the power 4. And strong coupling means the lambda large. Okay? Because the n have already factored out, so your coupling just lambda.
Oh, I see.
Yes?
So in this phi triangulation, so the propagator integration will become the space-time integration.
Hmm?
But I just wonder how the propagators integrate to match to the space-time integration.
Yeah. So the propagator, propagator you do in the standard way. You just write down your propagator.
Yeah.
And then you try to repackage that. The question you said whatever your rule, Feynman rule is, you just do that Feynman rule, and you write down this expression is something very complicated. And then you say, can I find some geometric interpretation of that? Yeah, what I'm saying is that doing from this perspective is very hard because you don't know what thing to because you don't know what thing to compare. And this is first. And second, you expect the geometric picture emerge only in those very complicated diagrams. And those complicated diagrams we don't know how to deal with. And those because they only emerge in the strong coupling limit, but in the strong coupling limit we don't know how to deal with that. And so that's why it's also difficult. But nevertheless, for some very simple series, say if you don't consider the Yang-Mills series, you don't consider gauge series, but suppose if you consider some matrix integrals, say for very simple systems, say for simple systems, like a matrix integral, so this structure, emphasize that this structure only have to do with you have a matrices, okay? And you can have matrix valued fields, or this structure will emerge you only have a matrix integral. So there's no field at all, just have a matrix integral. That same structure will also emerge. Yeah, for example, I can consider a series, say, have a series like this. Something like this. I can have a series like this, okay? And M just some Hermitian matrices. So this is just integral. And the same structure will emerge also in this series when you do Lagrangian expansion. Okay, when you do Lagrangian expansion. So that structure have nothing to do. You can do it for but this is something. So matrix integral is much simpler, say, than a field series, because you have much less degree of freedom. So for simple systems like say a matrix integral, or a matrix quantum mechanics, actually you can actually guess the corresponding string theory. Can guess the corresponding string theory. Because also the string theory in that case is also very simple. You can guess very simple string theory. But it's not possible for field theory. It's not possible for field theory. Yes?
So what do you mean by matrix quantum mechanics? Like that, okay.
So this is a matrix integral.
Yes.
And I can make it a little bit more complicated. So I make this M to depend on T. And then this becomes a matrix quantum mechanics. Say trace M dot square plus M square, say plus M4. Then this becomes a matrix quantum mechanics because you only have time. And then I can make it more complicated. I can make M dxt Tx. Then this becomes 1 plus 1 dimensional field theory.
So in what context does matrix quantum mechanics come like this?
I mean, just as some toy model.
Oh, okay.
Yeah, I'm just saying, this is a very difficult question.
Yes.
You say, I don't know how to deal with field series. Then let's start with a simple system.
Sure, okay.
And then just try to use this philosophy, can see whether I can do it for a simple system. And then you can show that this philosophy actually works if you do a matrix integral or matrix quantum mechanics.
Okay.
Yeah, simple enough matrix integral and matrix quantum mechanics. Okay. And if you want references, I can give you references regarding this. There's a huge amount of works, thousands of papers written on this subject. In the late 80s and early 90s. So those two examples just to show actually this philosophy works. I just show this philosophy works, okay? But it's not possible if you want to go to higher dimensions. Yeah, actually there's one paper, let me just write it here. So there's one paper explains the philosophy. So here I did not give you many details. Say how you write this G down, how you in principle can match with this thing. With another maybe 1 hour, you can make this discussion a little bit more explicit, but I don't have time. But if you want, you can take a look at this paper. So this paper discusses the story for the matrix quantum mechanics. But in the section 2 of this paper, so this is a paper by Kleblov. So in the section 2 of this paper, it explains this mapping of Feynman diagrams to the string action and this discretization picture. Give you a nice summary of that philosophy with more details than I have given to you. So you can take a look at that. And this paper also has some other references. If you want to look at it, you can take a look at it. Okay. Any questions? Yes?
Historically, who was the first to realize this connection between the surfaces and topology of Feynman diagrams?
Sorry?
Who first realized this relation between topology and...
So already, of course, already when 't Hooft, when he invented this Nagian expansion, he already noticed that this is similar to string theory. So he already commented on that. And but for many years, people did not make progress. For many years, people did not make progress. But in the late 80s, in the mid to late 80s, people start thinking about the question from this perspective, not from that perspective. So they start think about also from this perspective, because the string theory just typical string theory are hard to solve, etc. So people think maybe we can actually understand or generalize our understanding of string theory by discretize the worldsheet, and by also discretize the worldsheet, and then you just integrate over all possible triangulation, etc. And then they realize that thing actually is like summing over Feynman diagrams, and then for the very simple situations, say like say if you have only a matrix integral, actually you can make the connection explicit. Yeah. So that was in the late 80s. So people like McDowell or Kazakov, etc., they were trying to explore that. Other questions?
I'm having trouble seeing how the sum over all triangulations of genus H surfaces, how does that correspond to the discrete version of summing over all surfaces?
Right.
Genus H, I mean, that's the discrete sum over all possible genus H, right?
Yeah. I think this is the example. Let's consider a torus. So a torus is a box with this identified with this and this identified with that. Okay. Yeah. Let me first just draw the simplest partition. Yeah, just draw like that. Let me just look at these two things. Say suppose I give each box. Say if I specify each box, give a unit area, give a unit, okay? And I do this one, I do that one, or I do some other ways to triangularize it, then corresponding to give a different metric to this surface. And then corresponding to integrate over all possible metric on this surface. And integrate over all possible metric on this surface, you can interpret as integrate all possible surfaces.
How about in the case of the strings, for example, we would sum over the torus here and the torus there and the torus there?
No, you're only summing over single torus. No, what do you mean by summing over torus here, torus there?
I thought like in the path integral in the case of the string theory, for example.
No, you're only summing over a single torus. You're only summing over a single surface, but all possible ways to draw that surface. So what you said about the summing torus here, summing torus there, the corresponding what we call the disconnected amplitudes. And then you don't need to consider them in physically. Physically disconnected amplitude you can just exponentiate what we call by connected amplitude. And you don't need to do that separately. So once you know how to do a single one, and then disconnected one just automatically obtained by explanation.
Well, if the two configurations are homologous, then they are sort of the same thing. And we just count them once. Maybe on this side of this thing doesn't matter.
Sorry? No. Here we are only, here the metric is matters. The geometry matters. It's not just topology.
But then, the Feynman diagram, does Feynman diagram care about this geometry?
Yeah, just the key is that the propagator of the Feynman diagram essentially encodes those geometries. And of course encode in a very indirect way. Yeah, just read this part. This section only have a few pages, but contain a little bit more details than what I have here. Requires maybe 1 more hour to explain this in more detail. And which, this is just said. I just want to explain this philosophy. I don't want to go through the details and how you do this. Okay, good. So now let me just mention a couple of generalizations. So mention a couple of generalizations. I think I'm right. So the first thing you already asked before, I think maybe both you have asked. Let me just mention them quickly. And if you are interested, I can certainly give you reference for you to read about them, or you can do it or I can put it in your PSET. And so far, it's all matrix valued field. Okay. But if you consider a theory like, or in other words, in the mathematical language, say it's in the joint representation. It's in the joint representation of the, say, because our symmetry is a UN, it's a UN gauge group. Okay? UN gauge group. But you can also, for example, in QCD, you also have quarks. So you also have field in the fundamental representations. So can also include, say, field in the fundamental representation. So rather than matrix valued, they are n vector. Okay, they are n vectors. So for quarks, of course, for the standard QCD, n will be 3. So you have 3 quarks. You have 3 different color quark. And so then in your Feynman diagrams, in addition to have those matrix lines, which you have a double line, and now here you only have a single index, okay? And then you only have a single line. So the propagator of those quarks, you just have a single line. And then also in your Feynman diagram, you can have the loops of the quarks, etc. So you can again work this out, and then you find there's a very nice Lagrangian expansion. Very nice Lagrangian expansion. And then you find the surface, the diagrams, the Feynman diagrams. Now you find in this case, the Feynman diagrams can be classified by 2D surfaces with boundaries. Okay. So essentially, you have, for example, and let me just say, for example, this is the vacuum diagrams for all the vacuum process. Say, then you can say for the all the vacuum diagrams, and then then they can all be classified. So previously, when you have a matrix valued field, then all your vacuum diagrams, they corresponding closed surfaces, say sphere, torus, etc. But now if you include the quarks, then those surfaces can have boundaries and corresponding to the quark loops, etc. And then they can be classified. So this also have a counterpart. If you try to map to the string theory, so this corresponding to string theory. A string theory with both closed and open strings. Okay. And so essentially those boundaries give rise to the open strings. So here it's all closed string, it's all closed surface. But now you can, by adding the open string, and then you can again have the correspondence between the two. Okay. So all the discussion is very similar to what we discussed before. We just apply all this the same philosophy to the quarks. Yes.
Can we do the same trick on string theory and find some sort of expansion which then will map to some higher order surfaces? S3 type, 3 torus, 3 spheres.
Sorry, say it again.
I mean, from lines in Feynman diagrams, we move to string theory to surfaces.
Yeah.
If there's some sort of expansion from surfaces, just they go one more step up.
You mean higher dimensions,
Yeah.
not strings?
Yeah, from there.
Yeah, that will become. Of course, that's a lateral idea. So that would be corresponding to, say, you can consider rather strings, you can consider two-dimensional surface, a two-dimensional surface moving in space-time. And then that would corresponding to so-called the membrane theory. But that theory turns out string is a nice balance. It's not too complicated or not too simple, and give you a lot of structure. But when you go to membrane, then the story becomes too complicated, and nobody knows how to, say, quantize that theory. Yeah. So the second remark is that here we consider UN. So here our symmetry group is UN. Because our field, because of phi there is Hermitian. So when you have a Hermitian matrix, then there's a difference between the two indices. So we call one, we put one up and one down. So they are propagators. Then these two say this to the lines with arrows because we need to distinguish up and lower indices. Okay, distinguishing two indices. But you can also consider, for example, phi is a symmetric matrix. Say it's a real symmetric matrix. Say real symmetric or real antisymmetric. In those cases, then there's no difference between the two indices. And then when you draw a propagator, so in this case, the gauge group, the symmetry group, would be, say, SON, say, or SPN, etc. SPN, etc. And the propagators, they will no longer have orientations. Okay, they will no longer have orientations. Yeah, because you can no longer. Yeah, so this will give rise. Yeah, so let me write it closer. So this will give rise to unorientable surfaces. Okay, will give rise to, say, for example, to classify the diagrams, you can no longer just use orientable surfaces. You also have to include the non-orientable surfaces to classify the diagrams. And it turns out this also have a precise counterpart into unorientable strings, non-orientable strings. Actually, I think non-orientable. Non-orientable surfaces. Also non-orientable strings. Okay. Good. So after emphasizing how difficult it is, if we want to start with say QCD, and then try to find its string theory description, but let's still nevertheless try. At least try. Yeah, for okay. So let's just consider. So let's consider just so just take notch n generalization say of QCD. So this again would be some UN gauge theory, UN Yang-Mills theory, say in 3+1 dimensional Minkowski space-time. And can we say anything about the string theory description? Okay. So nevertheless, so maybe it's difficult, but let's try to guess it. Okay. So in physics, in many situations, a seemingly difficult problem, if you know how to guess it, actually you can get the answer. For example, quantum Hall effect, a fractional quantum Hall effect. You can just guess the wave function. So of course, the simplest guess. So this is some gauge theory in 3+1 dimensional Minkowski space-time. So now we say this is a string theory. So natural guess is that this maybe is a string theory. Again, in the 3+1 dimensional Minkowski space-time. Okay. So we just take what. So this would correspond to a stream propagating in this space-time. Okay. So as I said, when you write down a string theory, you first have to specify your target space, which the stream moves. The larger question would be should be the gauge series in Minkowski space-time, maybe the string theory should be, okay? And then you can just try to then you can just write down the simplest action. So maybe say nambu-goto action, which we wrote last time, okay? Or some say all Polyakov action. So so this nambu-goto action which we wrote the Polyakov. Yeah. Let me not worry about that. Yeah. For example, you can just guess. Say maybe this is a string theory also in the Minkowski space-time. Say consider the simplest action. This or the equivalent of this. Okay. Then at least what you could try. Now you have action. Now you essentially have this object. Now you essentially can compare. Okay. Now you can essentially compare. Say in QCD you calculate your Feynman diagrams and now just compare. But of course you still have the difficulty. Of course you have to go to strong coupling to see the geometric limit, etc. But in principle it's something you can do. But this actually does not work. Okay. This does not work. For the following simple reason. First, it has such a string theory. Say a string. So a string theory, actually, the remarkable thing about a string is that if you have a particle, you can put the particle in any space-time. But strings are very picky. You cannot put them in any space-time. And they can only propagate consistently, quantum mechanically consistently, in some space-time, but not in others. So for example, if you want to put a string to propagate in this 3+1 dimensional Minkowski space-time, then you actually find that the theory is mathematically inconsistent. So such a string theory is inconsistent. It's mathematically inconsistent, except for, say, d equal to 26 or 10. Okay, so 26 is you don't, just purely have this theory, and 10, say, if you also add some fermions. So such a string theory does not exist mathematically. So you say, oh, okay. You say, I'm a smart fellow. I can go around this. Because we want Minkowski space-time, because those gauge theory propagate in the Minkowski space-time, so this Minkowski space there must be somewhere. They cannot go away because all these group balls they live in this 3+1 dimensional Minkowski space-time. And if we want to identify the strings with those group balls, those strings must at least know some of this Minkowski space-time. And then you say, suppose you tell me that this string theory is only consistent in 10 dimension. But then let me take a string theory in 10 dimension. Which is self-consistent. But I take this 10-dimensional space-time to have the form of a 3+1 dimensional Minkowski time and times some compact manifold. Okay. Some compact manifold. And in such case, so if this is a compact manifold, then the symmetry of this space-time, say the space-time symmetry, still only have the 3+1 dimensional, say, Poincare symmetry. Then, because if you want to describe the QCD in 3+1 dimension, QCD has the Poincare symmetry. You can do Lorentz transformation, and then you can do rotation, or you can do translation. The string theory should not have more symmetries or less symmetries than QCD. They should have the same symmetries because they're supposed to be the same description. But if you take the 10-dimensional flat space, a 10-dimensional Minkowski space, of course, it's not right because the 10-dimensional Minkowski space have 10-dimensional translation and 10-dimensional Lorentz symmetry. But what you can do is that you take it this 10-dimensional space to be a form of the 3 plus 1 dimension Minkowski space-time and times some additional compact manifold, and then you have solved the symmetry problem. But except this still does not work because the string theory, as we know, always contains gravity. And if you put the string theory on such a compact space n, that will always lead to a massless spin 2 particle in this 3 plus 1 dimensional part. But from Weinberg-Witten theorem we talked in the first lecture, in the QCD you are not supposed to have a 3 plus 1 dimensional massless spin 2 particle. Okay? And so this won't work. Okay, so this won't work. Because this contains in 3 plus 1 dimensional space, which is not present. Okay? Or in a larger version of QCD. So this does not work. So what to do? Yes?
So does this just mean like that it's mathematically inconsistent?
No. This does not mean it's mathematically consistent. It just means this string theory cannot corresponding to the string theory described QCD. The string theory description, the equivalent string theory for QCD cannot have this feature. Yeah. Just say this cannot be the right answer for that string theory. This string theory is consistent. Yes.
So is that you're saying that if there is a massless spin 2 particle in that string theory, there has to be a counterpart in the QCD?
That's right.
If there is not allowed this,
yeah,
that won't work.
Yeah, then this cannot be a description of that. From Weinberg-Witten theorem, we know in QCD there's no massless spin 2 particle. Yes.
I thought we have talked about maybe we can put spins 2 particle in QCD in a different dimension, different space.
Yeah, we will go into that. But now they're in the same dimension because this Minkowski 4, this will have the gravity. This will have a. This will have a. Because this is a compact part, doesn't matter. So in this part there is a spin, massless spin 2 particle. This is not present in QCD. So what can you do? So most people just give up. Most people give up. So option, so other than give up, the option is, say maybe this action is too simple. Maybe you have to look at a more exotic action. Okay, so this is one possibility. And the second possibility is that maybe you need to look for some other target space. Okay. But now, once you go away from here, everything else is like now becoming, say, search little in the ocean because then you don't have much clue to do. We just say your basic guess just cannot work. So for many years, even though this is a very intriguing idea, so people could not make progress. But now we have hindsight. So we know that even this maybe cannot be described by a 4-dimensional. Yeah, so if this, so even though this cannot have a, say, so this cannot have a, say, massless spin 2 particle in this 3 plus 1 dimensional Minkowski space-time, maybe you can still have some kind of graviton in some kind of a 5-dimensional space-time. Okay, you have some 5-dimensional in a different dimension. So there was some rough hint. Maybe you can consider it as a 5-dimensional string theory. But so let me emphasize, when I say 5 or 4, I always mention the non-compact part. So the compact part it doesn't count, because compact part just goes for the right. What determines the properties, say, of massless particle, etc., is the uncompact of the space-time. So yeah, because this is a 10-dimensional space-time, this is already not the. So maybe we hint for hint for a string theory. In 5-dimensional, uncompact.
5 means the 4 plus 1?
Yeah.
Okay.
In 4 plus 1. Uncompact space-time. Okay. Compact. Yes?
When you say compact, do you mean mathematical definition of compactness?
Sorry?
When you say compact, do you mean the mathematical definition of compactness?
Yeah, that's right. Yeah, I just say say with a finite volume. Just for our purpose here, we can do it simply. Just let's imagine have compact always have a finite volume, for example. Yes.
Why can't we just ignore the compact dimensions? Is there any like condition on like how big they're about to be or something? Like limit?
Yeah. Just when you have so if you know a little bit about this thing called the Closed-Klein theory, and you know that the compact part, yeah, the thing is that if you have a theory with uncompact and the compact part, and then most of the physical properties is controlled by the physics of uncompact part, and this will determine some details like the detailed spectrum, etc. But the kind of thing we worry about whether you have, there's a matter spin 2 particle, etc., will not be determined by this kind of thing.
Is there any like volume limit on the compact part, like maximum?
No, as far as I have a finite volume.
Just finite, but it can be like large.
No matter how large, this have infinite. It's always much smaller than this one. Yeah, but large is always relative. It's always relative. Yes.
Tracking back a little, is there any quick explanation for why 26 and 10 are special, or is it very complicated?
Okay. No, it's not complicated. Actually, we were going to do it in the next lecture. Yeah, next lecture we will see 26, but maybe not 10. Yeah, 10 is a little bit more complicated. Yeah, most people voted for my option 1, so that means you will be able to see the 26.
Great.
Right.
Those numbers 26 and 10, they're specific to this nambu-goto action, right? So for other action will be something else.
It's specific for the actually, the specific for the nambu-goto action is 26. And for the 10, you need to add some additional fermions and make it into a so-called superstring, then become 10. And this even this 26 one is not completely self-consistent. And anyway, there's still some a little bit tiny problem with this. Anyway, so normally we use 10. Yeah. Okay, so now then there's some tantalizing hints for the, say maybe you cannot do it for the with a 3 plus 1 dimensional uncompact space-time. Maybe you can do a 4 plus 1 dimensional uncompact. So the first is the holographic principle. We have length. Holographic principle, we have length, because we say if we want to describe a theory with gravity, then this gravity should be able to be described by something on its boundary. And the string theory is a theory with gravity. So if the string theory should be equivalent to some kind of QCD, some kind of gauge theory without gravity, And then from holographic principle, this field theory maybe should be one lower dimension. Okay? Be one lower dimension. Isn't the logic here clear?
Wait, can you say that again?
So here we want to equate non-GN QCD
Yes.
with some string theory.
Right.
But string theory we know contain gravity.
Yes.
At least from all our experience contain gravity. And, but if you believe that the gravity should satisfy holographic principle, then the gravity should be equivalent, according to holographic principle, gravity in, say, in d-dimensional space-time can be described by something on its boundary, something one-dimensional lower.
So, but I thought the holographic principle was a statement about entropy.
No, it's a state started from a statement about entropy, but then you do a little bit of leap. So what I call a little bit a conceptual leap is that or a little bit leap of faith is that you promote that into the statement is that the number of degrees freedom you needed to describe the whole system.
I see. Okay.
Yeah. So the holographic principle is that for any region, if in the quantum gravity theory for any region, you should be able to describe it by the degrees freedom living on the boundary of that region. And the degrees freedom living on the boundary of that region, then it's one-dimensional lower.
Wait, so can I ask one question about
Yeah.
that? Like if I have some region, some volume in space, some like closed ball or something, and I live in a universe which is, for example, a closed universe, like maybe I live on some hypersphere or something like this, then how do I know whether how do I know that the information is encoded? How do I know whether I'm inside the sphere or outside of the sphere? Like, for example, we say that the entropy that has to do with the sphere basically tells you about how much information can be contained inside the sphere.
Yeah.
But if you live in a universe which is like closed or something, then you don't know whether you're inside or outside the sphere.
Yeah, but that's a difficult question.
Okay.
Yeah, if you talk about closed universe here, we are not talking about closed universe.
I see.
Yeah. Yes.
But I thought the holographic principle is that the number of degrees of freedom inside the region is actually bounded by the area of the.
Right. It's bounded by.
Yeah, but why is it the degree of freedom? You said the degree of freedom living on the boundary.
Yeah, there are several formulations of that. First is that the total number of degrees freedom in this region is bounded by the area, and then you can go to the next step. Is that maybe the whole region can be just described by the degrees freedom living on the boundary of that region.
Is that because say the state density on the boundary is like the state on the boundary is proportional to the area of the boundary?
Yeah, exactly. That's right.
Okay.
That's right.
So here our goal is to recover the large M theory in 3+1 dimensions without gravity. So we have no gravity in 3+1.
That's right. That's right. Yeah. So if that is supposed to be equivalent to the gravity theory, and the gravity satisfies the holographic principle, and then the natural guess is that this non-gravitational field theory should live in one dimension or lower. Okay. So this is one hint. And the second is actually from the consistency of string theory itself. Okay. So this is a little bit technical. Again, we will only be able to explain it a little bit later when we talk about more details about string theory. It turned out even though the string theory in this space is inconsistent, but there's a simple way. It's not a simple way. Yeah, so what's happening is the following. So if you consider, say, a string propagating in this space-time, and there's some symmetries on the worldsheet. And only in the 10 and 26 dimension, those symmetries are satisfied quantum mechanically. And in other dimensions, those symmetries somehow, even though it's classically it's there, but quantum mechanically it's gone. And those symmetries become, because they're gone quantum mechanically, then they lead to inconsistencies. And turns out they lead to inconsistency. It turns out there's some other way you can make that consistent to make that symmetry still to be valid is by adding some new degrees freedom. Okay, it just there's some new degrees freedom dynamically generated, and that new degrees freedom turned out to behave like additional dimension. Okay, this will make no sense to you. I'm just saying you a consistency of string theory actually sometimes can give you one additional dimension.
What is the difference between these inconsistencies you're talking about and like anomalies in quantum field theory?
Yeah, it is anomalies.
Okay.
Yeah, but here it's called gauge anomalies.
Okay.
Yeah, it's gauge anomalies. Is that the local symmetry anomalies, which is inconsistent.
So just maybe this is not the time to ask it, but are the degrees of freedom that you need to like save you from this inconsistency problem? So they could, if they look like, do they have to be extra dimensions of space, or like, or what I'm saying is that if we need to do string theory in 10 dimensions, is it really 4 dimensions plus 6 degrees of freedom, or are they actually 6 quantified spatial dimensions?
No, this is a very good question. Say if you have, say, this is something we will be a little bit more clear. Just even oh, it's very late. Even the second part of this lecture, is that here you have 6 degrees 4 degrees freedom. You have 6 degrees freedom.
Yeah.
But turns out, if you only consider this guy, then this 4 degrees freedom by itself is not consistent. Say there's some violation of the symmetry at the quantum level. And then you need to add more, and then one more then corresponding to have extra dimension. Yeah. Anyway, we can make it more explicit in next lecture. Okay. Yeah. Here I just throw a remark here. Anyway, this guy, this is purely hindsight. Nobody have realized this point, this first point. Nobody have realized it before this holographic duality was discovered. Okay, nobody really made this connection. Nobody made this connection. And this point, from this point, saying there should be a 5-dimensional string theory describing spin 2 particle, describing a gauge theory, that was made just before the discovery. I will mention that a little bit later. Anyway, so now let's, let me just maybe finish this, then we have a break. So now let's consider, suppose there's a 5-dimensional space-time string theory in some 5-dimensional space-time, say 4 plus 1 dimensional space-time, say describe QCD. Then what should be the property of this y? Okay, so this y denotes this some manifold y. Okay. So as I mentioned, it must have at least all the symmetries of the QCD, but not more. Should have exactly the same amount of symmetries. So that means you must have the translation and the range symmetries of QCD. Okay. So that means the only metric I can write down must be of this form. The only metric I can write down, the metric must have this form. So this AZ is just some function, and Z is the extra dimension to a Minkowski space-time. And this is a Minkowski metric for 3 plus 1 dimension.
You mean it's like a project to 4 dimension? We have to get the Minkowski space.
Yeah, I just say whatever this space, whatever is the symmetry of this space. So the symmetry of this space-time must have the Poincare, must have all the symmetry of the 3 plus 1 dimensional Minkowski space-time. Then the simplest way, essentially the only way to do it is just you put the Minkowski space-time there as a subspace. And then you have one additional space, and then you have one additional dimension. And then, because you have to maintain the symmetry, then with a little bit thinking, then you can convince yourself the only degrees freedom, the only additional degrees freedom in the metric you can allow is an overall function, say the function of this z, and nothing else. Okay.
But can that be also kind of a scalar in Minkowski space?
Yeah. Let me just say this is most general metric consistent. With 4-dimensional, 3 plus 1 dimensional Poincare symmetry. Okay.
Why this additional dimension always in the space part? Can it be in the time-like part, like 3 plus 2?
Both arguments suggest it's a space part. So because this is just the boundary of some region, that's a spatial dimension reduction, not the time.
Okay.
Yeah. So is this clear to you? Because you want to have a Minkowski space-time, so you must have a Minkowski here. And then in the prefactor of the Minkowski, you can multiply by anything, any function, but this function cannot depend on the x. It can only depend on this actual dimension. Because if you have anything which depends on capital X, then you have violated the Poincare symmetry. You have violated the Lorentz symmetry. You have violated translation in the X. Then the only way, so the only function you can put before this Minkowski space-time is a function of this additional dimension. And then by redefining this additional dimension, I can always put this overall factor in the front. Yeah, so this tells you that this is the most general metric. Okay? So if it's not clear to you, think about it a little bit afterwards. So this is the most as you can do. So that's the end. So you say you cannot determine AZ, etc. So this is as most you can say for the QCD. Okay. But if the theory, if the field theory is scale invariant, say a conformal field theory, that normally we call CFT, okay? Say a conformal field theory. Then we can show this metric. So let me call this equation 1. Then 1 must be anti-de Sitter space-time.
So if we're going to have Pleyel symmetry on the boundary as well, it forces it to be that form.
Yeah, I'm going to show that. Yeah. So if the field theory is scale invariant, that means that the field theory have some additional symmetry, should be satisfied by this metric. And then I will show that this additional scaling symmetry will make this to precisely a so-called anti-de Sitter space-time. Okay?
Field theory in the 3 plus 1, right?
Yeah, right. If the field theory, say the QCD does not have a scale, it's not scale invariant. So I do not say QCD anymore. Just say suppose some other field theory which have a Lagrangian expansion, which is also scale invariant, and then there must be, then the corresponding string theory must be in anti-de Sitter space-time.
Are we ever going to connect back to QCD, or is that it?
No, that's it. No, we will come back to QCD, but somewhat indirect way. Yeah, not to your real life beloved QCD.
So no one solved that problem still?
Yeah, no one solved that problem yet. Yeah, so you still have a chance.
All right.
So the argument is very simple. So let me just say it, then we'll have a break. Then we will done. Yeah, I think I'm going very slowly today. So scale invariant theory is invariant under the scaling for any constant lambda. Okay. So scales invariant theory should be invariant under such a scaling. And then now we want to require this metric also have some this scaling. So okay. So now require 1 also have such scaling. Such scaling symmetry. Okay, so we just do a scaling x mu, go to lambda x mu. And then this term will give me additional lambda square. So we see in order for this to be the same as before, the z should scale the same. Okay? So in order for this to be, so we need the z's to scale as the same. In order I can scale this lambda out. After I scale this lambda out, I also need that a lambda z should be equal to 1 over lambda az. Okay? So the scaling symmetry of that equation requires these two conditions. So under scaling of z, this a lambda z should satisfy this condition. Okay? Then the lambda will cancel. So this condition is important because we need to scale them homogeneously. Otherwise, of course, lambda will not drop out. And the second condition, just make sure lambda is cancelled. Okay, is it clear? So now, this condition then just determined that az must be a simple power. Must be written as r divided by z. So r is some constant. Okay? And now we can write down the full metric. So now I've determined this function up to an overall constant. So the full metric is dx squared equal to r squared divided by z squared, dz squared plus eta mu mu dx mu, dx mu. And this is precisely a ds metric written in certain coordinates. And this r, then is just the curvature radius of ADS. So if you don't know about anti-de Sitter spacetime, it doesn't matter. So this is the metric, and the name of this metric is anti-de Sitter. And later we will explain the properties of the anti-de Sitter spacetime. So now we reach a conclusion is that if I have a large M conformal field theory in Minkowski d-dimensional spacetime, so this can be applied to any dimensional, so not necessarily 3 plus 1. In D, so this, if it can be described by a string theory, should be string theory in ADS d plus 1. Okay? And in particular, the 1 over n here is related to the G string here. Okay, the string coupling here. So this is what we concluded. Yes?
So all we showed is that there is no obvious inconsistency with that correspondence.
What do you mean there's no obvious?
As in, like, we didn't illustrate in any way that they...
Sure. I'm just saying this is a necessary condition.
Right, so at least that is necessary.
Yeah, this is a necessary condition. So if you can describe a large N CFT by a string theory, and it should be a string theory, yeah, this proposal works. This proposal passed the minimal test.
Question. So when Maldacena presumably actually did figure this out. You said that this resulted of the holographic principle, like
Yeah.
it was just figured out right before he did it. Was he aware of the holographic?
No. Here is what I'm going to talk. So Maldacena, in 1997, Maldacena found precisely. In 1997, Maldacena found a few examples of this, precisely realized this. And not using this method, using some completely indirect way, which we will explain next. So he found this through some very indirect way. But in principle, one could have realized this if one kept those things in mind. So now let me tell you a little bit the history, then we will have a break. Then we can go home. So it depends on whether you want a break or not. Maybe you don't want a break. Yeah, let me tell you a little bit history. So in just to save time, let me not write it down, just say it. So in late 60s to early 70s, so string theory was developed to understand strong interactions. Okay, so understanding strong interactions was the problem at the time. People were developing string theory to try to understand strong interactions. So in 1971, of our friend Frank Wilczek, and other people, they discovered the symptotic freedom, and then established, say the Yang-Mills theory as the description of strong interaction, which now have our QCD. And so that's essentially eliminated the hope of string theory to describe QCD. Okay? Because the QCD seems to be very different. Eliminated the hope of a string theory to describe strong interaction, because the QCD, SU3 gauge theory, is very different from the string theory. So people soon abandoned the string theory. So now we go to 1974. So 1974, a big number of things were discovered in 1974. So 1974 was a golden year. So first is to hope to realize his Lagrangian expansion, and realize this is actually looks like a string theory. And then, completely independently, Shirk, Schwartz, and Yulia, they realized that string theory should be considered a theory as a gravity rather than a theory of strong interaction. So they realized actually, it's ironic, people started doing string theory in the 60s and 70s, etc. But only in 1974, people realized, string theory always have a gravity and should be considered a theory of gravity. Anyway, so in 1974, they realized that string theory should be considered as a gravity. So that was a very, very exciting realization. Yeah, because then you can have quantum gravity. But by that time, people have given up on string theory. So nobody cared about this important observation. So also in the same year, in 1974, Hawking discovered his Hawking radiation, and then established that the black hole mechanics is just it's really a thermodynamics. Then really established that black hole is a thermodynamic object. And in 1974, there's also another important discovery, which is related to MIT, so that's why I mention it, is that the people first really saw quark experimentally. Is that our friend, colleague Samuel Tin at the Brookhaven, which they discovered the so-called charmonium, which is the bound state of the charm quark and the anti-charm quark. And because the charm quark is very heavy, so they form like a hydrogen-like structure. So in some sense, the charmonium is the you first directly see the quarks. And actually, even after the 1971, after asymptotic freedom, many people did not believe QCD, did not believe quarks. They say, if there's a quarks, why don't we see them? And then in 1974, Samuel Tin, they discovered this charmonium in October, and so people call it the October Revolution. Do you know why they laugh? Okay. Right. Yeah. Anyway, yeah. The Cold Revolution. Right. Yeah, because I saw your emotions, I think you have very good the composure. Anyway, in the same year, in 1974, Wilson proposed what we now call the lattice QCD. So he put the QCD on the lattice, and then he invented, and then he developed a very beautiful technique to show from this putting QCD on the lattice that actually the quark can be confined through the strings. So the quarks in QCD can be confined through strings. And then that essentially revived the idea maybe the QCD can be a string theory because the quarks are confined through the strings. It's all happened in 1974. So then I mentioned, say, in the late 80s and early 90s, people were looking at these so-called matrix models, say matrix integrals, etc. Then they show they related to some lower dimensional string theory, but nobody. Yeah, they showed this related to some kind of lower dimensional string theory. And then in 1993 and 1994, then 't Hooft had this crazy idea of this holographic principle. He said maybe things about the quantum gravity can be described by the things living on the boundary. And it's a crazy idea. Very few people paid attention to it. But the only person who the only person who picked it up is Lenny Susskind, and then he tried to come up with some thought experiment to show that that idea is not so crazy. Not so crazy. So actually, Susskind wrote a very sexy name for his paper. It's called "The World as a Hologram," yeah. Anyway, so that paper received some attention, but still people did not know what to make of it. And then in 1995, Polchinski discovered so-called D-branes, and discovered the so-called D-branes. And then we go to 1997. So in 1997, first in June, so as I said, that QCD may be some kind of string theory. This idea is a long idea, starting from the 't Hooft Lagrangian expansion, and also from the Wilson's picture of confining strings from the lattice QCD, etc. But it's just a very hard problem. From QCD, how can you come up with a string theory? Just very hard. Very few people were working on it. So in 1997, in June, Polyakov finally, he said, had a breakthrough. He said that this consistence of string theory give you one extra dimension. You should consider a 5-dimensional string theory rather than a 4-dimensional string theory. And then he gave up some arguments anyway. And he almost actually write down this metric. Maybe he already wrote down this metric. I don't remember. Anyway, he was very close to that. But then in November, the Marcina came up with this idea CFT, and then he provided explicit examples of certain Lagrangian gauge theories, which is scale invariant, and some string theory in certain anti-de Sitter space-time. And as I said, through the understanding of these D-branes, But even Marcina's paper, he was still thinking from the picture of Lagrangian gauge theory corresponding to some string theory. He did not make the connection to the holographic principle. And but very soon, in February 1998, so Witten wrote the paper, and he made the connection. He said, this is precisely the holographic principle, and this example, then he said, this example is precisely the holographic principle Susskind and 't Hooft was talking about. Yeah. So that's a brief history of how people actually reached this point. So the next stage, what we are going to do is to try to derive this thing. So now we can have, as I said, we can have two options. We can just start from here. So assuming there is some CFT, is still is equivalent to some string theory, and then we can see how we can develop this further, and this is the one option we can take, and another option is to really see how this relation actually arises from string theory, and many people voted for the second option, which in my email is option 1. So you want to see how this is actually deduced from string theory. So now we will do that. Okay. But I should warn you, there will be some technicality you have to tolerate in order to see how this is derived. Okay? So we do a lot of 20 minutes today? Without break? Good, okay. Yeah, next time I will remember to break. Okay. So now we are going to derive this. So first, just as a preparation, I need to tell you a little bit more about string theory. In particular, the spectrum of closed strings, closed and open strings. And so this is where the gravity, and from the closed string you will see the gravity, and from the open string you will see the gauge theory. Okay. We'll see a gravity and gauge theory. So this is the first thing we will do. So the second thing we will do is to understand the physics of deep branes. So deep brane is some object in string theory, and it turned out to be play a very, very special role to connect the gravity and the string theory. Okay, connect the gravity and the string theory, because this is the connection between the gravity and the string theory, and in string theory, this object of deep brane precisely play this role, which connect the gravity and the string theory. So that's why you can deduce such a relation. Okay, and yeah, so this is the two things we will do before we can derive this. Okay. So this is the say the rough plan we need to we will do before we can derive the this gravity. So first, let's tell you a little bit more about string theory. So at the beginning, just say some more general setup of string theory. So let's consider a string moving in the space-time which I denote by M, say with the metric ds squared equal to g mu mu. So this can depend on x, dx mu. Okay. So you can imagine some general curved space-time. Say mu and nu will go from 0 to 1 to d minus 1. Say d is total number of space dimension for this M. So the motion of the string, as we said quite a few times now, so the motion of the string is the embedding of the worldsheet to this space-time. So this is in the form of x mu sigma tau. Okay, you parameterize the worksheet by 2 coordinates. So I will also write it as x mu sigma a, and the sigma a equal to sigma 0, and the sigma 1 is equal to tau sigma. Okay. So I will use this notation. So now you imagine a surface embedded in some space-time, and this is an embedding equation because if you load those functions, then you know precisely how the surfaces are embedded. Okay. And because the original space-time have a metric, then there's an induced metric. On the worksheet. And this induced metric is very easy to write down. You just plug in this function into here. And when you take the derivative, you only vary the sigma and tau, because then that means you restrict it on the surface when you only vary sigma and tau. And then you plug this into there, then you can get the metric, then can be written in this form. This sigma a and this sigma b. Okay? So remember sigma a and sigma b, just tau and sigma. And this HAB is just equal to g mu mu x partial a x mu partial b x nu. Okay? So this is trivial to see. Just plug this into there. Do the variation with sigma and tau, you just get that and with that. Okay? So is it clear? So this nambu-goto action is the tension. Tension, we always write this 1 over 2 pi alpha prime EA. So alpha prime is the, say, parameter to have dimension square. So we often also write alpha prime as LS square. Okay. So alpha prime is just a parameter to parameterize the tension, to denote the tension of the string. So this area, of course, you can just write it as d square sigma. So again, I use the notation d square sigma just d sigma d tau. Okay, d square sigma minus delta h. Okay, so this is just the area because this is an induced metric. Induced metric on the worksheet. Then you take the determinant, then give you the area. So this is the standard geometric formula. So now let me call this equation 1. So I have a lot of equation 1 before, but this is a new chapter. Okay, so this is the explicit form of this nambu-goto action. But this action is a little bit awkward because involving the square root. It's considered to be another good thing in physics because when you write down action, because it's a non-polynomial. Okay, we typically like polynomial things because the only integral we can do is a Gaussian integral, and the Gaussian is polynomial. So this is inconvenient. So one can rewrite it a little bit. So I will write down the answer. So we can rewrite it in the polynomial form. And this polynomial form is called the Polyakov action. So I call it FP. Even though Polyakov have nothing to do with it. And this action can be written in the following form. And let me write down the answer, then I will show the equivalent.
Was it invented by Leonard Susskind?
No, it's not Leonard Susskind. No.
Why is it called the Polyakov effect? Why is it called the
Polyakov, actually Polyakov have something to do with it. Polyakov used it most effectively first. Okay, so you can rewrite it as that in this form. And the gamma AB is a new variable introduced. It's like a Lagrange multiplier. Okay? So let me point out a few things. So this structure is precisely just this HAB. So if you look at this structure, so this structure is precisely what I call the HAB. So now the claim is that in addition to original variable with just x, now I introduce a new variable gamma, and gamma is like a Lagrange multiplier because there's no kinetic term for gamma. So if I eliminate gamma, then I will recover this. Okay, so this is the claim. So now let me show that. This is very easy to see because if you just do the variation of gamma, AB, okay? So whenever I wrote indices in upstairs, it always means the inverse, okay? But this is the standard notation for the metric. So if you look at the equation motion, say by variation of this gamma AB, then what you find is that the gamma AB, just do the variation of that action, you find the equation motion for gamma AB is given by the following. So HAB, just that guy. And the lambda is arbitrary constant. A lambda is arbitrary function. Okay? This I'm sure you can do. You just do the variation, you find that equation. So now we can just verify this actually works. When you substitute this into here, okay, into here, so this gamma AB, when you take the inverse, then corresponding to the inverse HAB, inverse HAB contracted with this HAB just give you 2. And that 2, did I put the 2 in the right place? That give you 2. Then that have a 2. Yeah, I'm confused about 2 now. No, it's fine. Anyway, so this contracted with that. So gamma AB contracted with HAB give you lambda 2 divided by lambda 2 times 2, okay? Okay? Because you just invert this guy and invert the lambda and 2. And then square root minus gamma give me 1/2 lambda square root minus h. Okay? So sometimes I also approximate to, I will not write this determinant explicitly. When I write minus h means the determinant of h, and the minus gamma determinant gamma. Okay? So you multiply these two together, so this 2 cancels. And this 2 multiply this 4 pi alpha prime, and then give back that. Okay? So they're equivalent. Clear? So this gives you SNG. So now the key so now if you look at this form, so this really have a polynomial form for x, okay? So this so now let me call this equation 2. So equation 2, if you look at that expression, just has the form. So this is just like a 2-dimensional field theory. Has the form of a 2-dimensional scalar field theory. In the curved space-time, of course, the curved space-time is just our worldsheet sigma with metric gamma AB. Okay? Okay. So this is just like yeah, but key here. So sometimes 2 is called the nonlinear sigma model. Just traditionally, a theory of the form that equation 2 is called the nonlinear sigma model. Nonlinear because typically this metric can depend on x, and so dependence on x is nonlinear. So it's called nonlinear sigma model. But I emphasize both gamma AB and x are dynamical. Are dynamical variables. So that means when you do the path integral, say in the path integral quantization, you need to integrate over all possible gamma AB and all possible x mu. Not only integrate all possible x mu, but also integrate all possible gamma AB with this action. Okay? So this is a two-dimensional. So this is a two-dimensional world with some scalar field, and you integrate over all possible metric. So over all possible intrinsic metric on that in that world. So this can also be considered as 2D gravity, two-dimensional gravity coupled to D scalar fields. Okay. So now we see that when you rewrite this in this polynomial form, in this polyacol form, the problem of quantizing the string becomes the problem of quantizing two-dimensional gravity coupled to D scalar fields. Okay? So this may look very scary, but it turns out actually two-dimensional gravity is very simple. So it's actually not scary. So in the end, for many situations, this just reduced to, say, quantizing scalar field with a little bit subtleties. So yeah, let's stop here.